So most of the examples we looked at so far have dealt with exponential growth or logistic growth, but there are several times we'll have to look at exponential decay, one of which is when you're talking about radioactive isotopes. So radioactive decay is a really, really common application of exponential decay. So many elements have stable versions of themselves, like carbon-12 is very, very stable, but they have unstable isotopes, like carbon-14 is unstable. We usually measure the instability of an isotope by talking about its half-life, all right? So the half-life is the amount of time it takes for that substance to lose half of its current mass, all right? So if it starts with 100 grams and the half-life is 5 days, then after 5 days, it's going to be half of what it started. It's going to be 50, so on and so forth, all right? So let's look at radium-225. Radium-225 is a dang good isotope. If you were looking for something to put on your Christmas wish list, I would ask for radium-225, okay? It's a pretty good version of radium. It's not stable, though. Radium-226 is probably the most stable, and I say down here that radium-226 has a half-life of 1,600 years, which is a long time. Radium-225 is much less stable, okay? It's radioactive. So that means that it decays. Every 15 days, a little more than 2 weeks, it loses half of its mass. So you have to ask for it for Christmas and then play with it quickly, all right? If we start with a 6-gram sample, now that's a pretty nice sample of radium-225. You start with a 6-gram sample of radium-225, part A, how much of the original sample is going to be left after 12 weeks? After 12 weeks. Well, we could do one of two things. We can either wait 12 weeks. Well, first get ourselves 6 grams of radium-225 and then wait 12 weeks and measure it, right? Y'all want to do that? You want to wait 12 weeks? You'd be tardy to your other classes. If we stayed in here and waited, right? You can go 3 days without water, 3 weeks without food. We're going 12 weeks. And if we're waiting on that, we're going to have to start eating ceiling tiles just to survive. Look up at the ceiling tile. It looks like a giant wheat bin, doesn't it? Or maybe a Triscuit, like shredded. Yeah, those are a little dry. Those look less tasty than Triscuits. So let's not wait 12 weeks. That's the point I'm trying to make. Let's see if we can figure out mathematically. That way we can move on to another problem and not be tardy to our next class and eat whatever we want, right? Whether it's Triscuits with the wheat thin on top or whatever. So we need to come up with a mathematical model that describes it. So what letter do you want to use to represent the amount of radium present at any given time t? A, R, R-A. I heard A first. You call it R. We're going to go with A. Capital A for the amount as a function of t time. What is the initial amount that we're starting with? 6. Good. If we are going to write it based upon its half-life, what is a good decay factor to use? What good base do we use? 0.5 or 1/2, whatever you want. 0.5 is the same as 1/2. And we're going to raise it to the what power? If we're going to be measuring t, we have to say in what units. So what units do you want to use for t, first of all? Yeah, if we're measuring the half-life in days, let's just say we're going to measure t in days all the way through. So that's a very important declaration, all right? So then the exponent is going to be t divided by what? 15. 15. And there's the model. All right, so once we have the model, you can go ahead and type it into your calculator. Because now it's going to be like we did with logistic. I'm either going to give you an input value, a t value, and ask you to give me the y value, or I'm going to give you a y value and you're going to solve it graphically to give me the t value or the x value. So go to y equals. If there's anything in there, flush it out, hit clear. In y1, I'm going to type 6 times. And so you don't need parentheses. You could type in 0.5. That's a good version of 1/2. Caret, raised to the x. We always go with x for our independent variable, regardless of what we're calling it on our iPad, divided by 15. All right? So if you want, you can now set up a reasonable graphing window. And this is one of the most important parts of using a calculator. You should be able to establish a nice window without ever just doing trial and error on the graph. We're measuring time in days on the x-axis. So let's let our x-min be 0. And this is the only one that we're not quite sure of. If the half-life is 15 days, let's go out several half-lives. Let's go out 10 half-lives. Let's go out to 150. Okay, we can always adjust that later. We'll turn our x scale to 0. Y-min, we're measuring the amount in grams, so 0 is a good value. And in this case, since we started off with a 6-gram sample, we know it's not going to get bigger than 6 because it's decay. I'm just going to put in a 10 there. So I have a little space above the y-intercept of 6. Now, if you turn your y scale to 0 and you hit graph, you should see something that looks nice, okay? Exponential decay. If you needed to adjust your x-min, x-max, this is where you would do it. Okay, now we know we can answer questions with full faith and confidence. So the first question said, again, how much is left after 12 weeks? So 12 weeks is a time value, so I'm going to have to show that I'm plugging in a value for t. Now, do I plug in 12? No. We have to convert it. Very good. Our t in our equation is in days. So 12 weeks is equal to how many days? 7 times 12, which is 84. And y'all did that without a calculator, right? Awesome. The break didn't get to y'all. So A of 84, if you had to use a calculator, okay. You had it in front of you, right? It'd be a waste of a calculator if you didn't get to use it. All right, so now we're definitely going to use it. And there's 2 ways to evaluate it. The first way is, of course, what we did with the logistic. From the graphing screen, you could just hit trace and then type in 84. And as long as 84 is contained in your graphing window, which ours goes from 0 to 150, it should be okay. How many decimals do we report? 3. And you can either round or truncate. So 0, I'm going to go with the leading 0, 0.123 or 124. Those are the only 2 answers. And if we are going to truncate, which is what I pretty much do every time, and that's our final answer, we need to put units. What are the units here? Grams. All right, so that's one way to do it. The other way to evaluate it, which doesn't even require the graphing screen, is from the home screen. If you want to recall Y1, all you have to do is hit alpha trace, and that's the shortcut to all your Ys. Alpha trace number 1 gets you there. Or if you have the old 83, you hit vars right above tangent. You hit vars, which is variables. Click to the right to your Y variables. Hit enter for function mode, and there they are. So vars, Y vars, function, enter. If you then pull up Y1 and you open parentheses, type in an 84, close parentheses, it treats that like function evaluation. It's like A of 84. What's nice about that is you don't have to reestablish your X window to include the value you want. The window can still be from 0 to 10, and you can still get the answer. Notice if I tried to hit trace and type in what was left after 200 days, and I type in a 200, I'm going to get an invalid error here because my X window only went to 150. But if you did it from the home screen, no big deal. So there is an advantage to doing it on the home screen, but I don't care which one you do. All right, so that's part A. Part B, the follow-up question, the second question. How many days will it take then for our original 6-gram sample to decay to only 1 gram? Well, we know for sure it's going to take fewer than 84 days, right? Because we were way less than 1 there. So in part B, instead of giving you the t value, I'm giving you the amount value. So you're going to have to show A of t equal to 1. Oops, I put B equals. I didn't mean to do that. There we go. So that's what you show me, and then underneath there, you're going to have t equals, and then you just got to find it. So if I'm giving you the y value, remember, graphically, you graph the number in a different y equals. Our window has already been set up nicely. So if this were the first time you were graphing it, you'd want to go through this analysis to try and get a nice picture. When you hit graph, you should see them intersect. And because there's only 2 curves, and they only intersect once, if you go second trace number 5, you just hit enter, enter, enter. And there you go. You get t equals to 3 decimals, 38.774. Round or truncate, it's the same answer. And of course, then we put units on our final answer. That is what? Days. Yeah, days. So we wrote the model ourselves, but once we had the model, once we had the equation, it was very similar to the logistic equation in the previous section. For calculators, you always have to show what it is you're solving, what equation you're solving, or what expression you're evaluating is. So that is very important for the test. And of course, 3 decimals, round or truncate, and units on your final answer. All right, any questions or comments on example 8? That's radium-225, 15-day half-life. All right, example 9. Suppose now we have just a random radioactive sample. We don't know what element it represents. We don't even know how much we actually have to start with. But here's what we know about that radioactive sample. It loses 43% of its mass every 9,876 years. Woo! That's not very fast. What percentage of its mass will be left after 2,000 years? What should we do here? Wait 2,000 years? Set up a model, right? What's that? We got less than 2,000 years. Yeah, substantially less. No, that was example 8. We don't know what we don't know what the element is. No, I don't either. It just says suppose a radioactive sample loses 40. It could be, but I don't think it's radium-225 because it had a half-life of 15 days. This one has a half-life of 9876 years. So it can't be the same. Could it be radium-226, the most stable? No, it has a half-life of 1600. This half-life is much more stable. So this can't be radium at all. Just oh, it's not even a half-life. Yeah, you're right. I can't even talk about half-lives. It's 43% life is 9876. Yeah. So the point, Santiago, is we don't know what this is, nor do we care. We have enough information to write a mathematical model, believe it or not. All right. So I'm going to use R of T this time for radioactive amount that's left, because that was shouted out earlier. So I'm going to use R of T. We need an initial amount to work with here, and it didn't tell us how much we started with. So 100. Why 100, Rain?
I don't know.
Yes, you do know. That wasn't just an arbitrary guess. You do know.
It's a good number to start with because we don't really have to have it.
Yeah, 100 is a good number to start with. When in doubt, 100 it out, right? Yeah. We need to open a bank account. What do you want to put in here? I don't know. 100? Sounds good to me. Why is 100 a good number to work with here? We're dealing with percentages. Yeah, and percent means out of 100. So you could choose your initial amount to be anything in the whole wide world. 1, 100, 27.3. It's just easier if you work with 100. So we'll go ahead and go with that. 100 times. All right, so just like in the warm-up, if the decay rate is 43%, what is my decay factor? 0.57. Very good. 0.57 or 5700ths. Okay, because that's 100 minus 43 to get 57%, and then we convert it to a decimal. Raised to the T divided by, because it wasn't a half-life, it was a 0.57 instead of 0.5. But what's the exponent going to be if we measure in years? 9876. And we should probably declare that. Once you put that there, go ahead and declare what you're measuring T in. All right, so now we have our mathematical model. So now we can jump to part A. What percentage is going to be left after 2,000 years? So 2,000 is the value. I either plug it in for T or R of T. Which one? T. Any conversions to do here? Nope. So you're just going to put R of 2,000. And you could actually just type it into your home screen. 100 times 0.57 caret 2,000 divided by 9876. It'll give you the answer. But you're going to be using this more than once. And if you're going to be using it more than once, it's probably worth typing it into Y1. So I'll go ahead and do that. 100 times 0.57 raised to the X divided by 9876. Double check it, triple check it, make sure it's in there correctly. When in doubt, you can put parentheses around your base as well, okay? Especially if it's a fraction. Now, instead of graphing it to answer this question, I'm going to go straight to evaluating it on the home screen. Alpha trace is your shortcut. That's your F4 menu. The green menu is F4. So alpha trace gets the choices, and we want Y1, because that's where we typed in our equation. Open parentheses, 2 grand, close it, hit enter. You don't need the graph to do that. 89.240. If you're truncating or rounding, you need to show that third zero. And what would the units be? Well, the units on this would be grams or kilograms or pounds. We weren't really given any units of weight. But we haven't really answered the question yet either, have we? I'll just put units of mass here. The question said, what percentage of the mass will be left? So, blank percent is left. 89.240. How do you come up with that, Rain? Because it's out of 100. I'm glad you chose 100. Yeah, I'm glad you chose 100. If you had chosen like 5 for your initial amount, you would need to figure out, then you wouldn't have 89.24 as your answer, but you would need to figure out what percent of 5 is your final answer. It's real easy if you choose 100 to start with. All right, so Rain knew that in the beginning, and now if you didn't know that, now you do. We can all benefit from Rain's knowledge. Yeah. All right, thank you, Rain. So 89.240, don't forget to put the percent sign there. That's the unit is left. All right, part B. After how many years will the sample contain 22% of its original mass? 22% of its original mass. So we're going to have to set R of T equal to 22, question mark? Well, we want to know when it's going to contain 22% of the original mass. If the original mass was 100, what's 22% of 100? What's 22% of 100? 22. Man, I'm really glad we chose 100 as our initial amount. So we just put R of T equals 22. And that would be grams, pounds, kilograms, whatever. We don't know what the unit of mass is. But once you set it up like this, now you're going to have to solve it graphically. So we're going to go to Y2 and type 22. Now we're going to need a nice window. So I'm going to put 0 as my lower bound, or -1 as we did last week. If the half-life is 9876 years, I'm going to have to go out at least 9876 years. I'll go out 10,000, a little bit more. We can always adjust that one. Always adjust that. X scale 0, Y min 0 or -1. And since we started with 100, I'm going to go with 110. Because it's a decay function, not a growth, I know it's not going to get bigger than that. And of course, my Y scale to 0. And I'm looking to see where these two guys intersect. Do they intersect on my graphing screen? No, but is there hope for intersection? Yeah, we just have to look further to the right, don't we? Oh, I can't do it that way. You got to set your window. I was just trying to look down the screen. Let's set the X max to, you can set it to 20,000. I'm going to get a little bit more serious. I'm going to increase it by a factor of 10 by just adding a 0 at the end. Yeah. Oh, there you go. So if you wanted to increase it more slowly, 20,000, 30,000, that's fine. But here I can clearly see I have two equations, 1 point of intersection. I can find it now by going second trace number, 5. Enter, enter, enter. So underneath R of T equals 22, you now put T equals 26602.068. Right? R of T equals 22, and underneath there, T equals. Do we have units of that? That's years. That's years. Good. 26,602 and 68,000th of a year. We'll have exactly 22 grams of our original 100-gram sample, which is 22%. All right, you got the idea? So far, so good? Write the equation, and then I'll give you an input, you give me the output, or I give you the output, and you find where they intersect and give me the input. All right, here's an example ripped from the headlines. Something that's more relevant to y'all was 2011 in Fukushima, Japan. You remember that? What happened in Fukushima, Japan, 2011? Yeah, nuclear meltdown. A nuclear reactor went critical, okay? That was March 11th, 2011. Well, the original one, there was also a 5-mile island that happened, but this one was probably the most famous. April 26, 1986. Okay, 1986. The number 4 reactor at the nuclear power plant in Chernobyl, Ukraine, reached critical condition and exploded, essentially, in Chernobyl. Chernobyl. It released over 100 radioactive elements into the atmosphere. There forever and ever and ever. Some of these had relatively short half-lives and dissipated very, very quickly. Some did not. Some of the elements released into the air, iodine, strontium, cesium, those are perhaps the most dangerous. Iodine wasn't that big of a deal because the half-life for iodine is only 8 days. Okay? Only 8 days. How long has it been since 1986? More than 8 days. Very good. It's been about, the math class, 31 years. Okay? The other 2 elements that were pretty hazardous, strontium and cesium, have half-lives of 29 years and 30 years respectively. So notice we just inched past the half-life for those 2 critical, sensitive, radioactive isotopes of those cancer-causing elements. What happens if you're exposed to these? Well, iodine can cause thyroid cancer. Strontium can cause blood cancer, leukemia. Cesium can also cause birth defects and other types of cancers. They're all dangerous. The effects of cesium can harm the liver and the spleen. So here's what we want to do. The one in, by the way, I say here, the one in Fukushima rivaled Chernobyl. So very similar type of levels. But we're going to focus on these numbers here. Hypothetically, if 2,000 grams of cesium-137 were released at the Chernobyl explosion, 2,000 grams, how many grams of that cesium-137 are present there today? Well, cesium, remember, was the one that had the half-life of 30 years. So we know if 2,000 were released, since it's been 31 years, we were at 1,000 last year. It should be a little bit less than 1,000, right? But that's all we could tell. We want to figure out what it is to 3 decimals. So just like we did before, we need to write a mathematical model. So what do you want to use for a letter here for the amount of cesium? C? C of T is good. C for Chernobyl, C for cesium, whatever you want to do. So C of T, and we'll measure T in, bless you, years. Yeah. So what was the initial amount? 2,000. That goes right there. And the base, because this is a true half-life, is 0.5 or 1/2. And then T divided by the half-life, which is 30. Okay, so now we have a model with which to work. So now, on part A, we're going to go ahead and plug in. We'll just round. We'll just call it 31 years exactly. And if you plug that in, you get 1/2 to the 31 divided by 30. Now, when you plug it in by hand, you get this answer right here. You could just type this into your calculator on the home screen and get a 3 decimal equivalent of it. That's fine. We're going to go ahead and do it another way, though. The way we've been doing it, we're going to type the equation into Y1 and come up with a reasonable window here, because that's not just what we're learning about math and how to set up these models and how to model into real-life things. We're learning how to use the graphing calculator. And part of that is coming up with a relevant domain and range. All right, so the equation is 2,000. Now, if you want to use 1/2 instead of 0.5, that's fine. I would recommend parentheses, alpha y equals, bless you, 1/2, close parentheses, raised to the T divided by 30th power. So it's a lot more work. Okay, so 0.5 to the x divided by 30th is faster. But if your base was like 2/3 or something, you would want to write it as 2/3 and not like 0.6666666, because 2/3 is more exact. So now that we have our model, let's go ahead and go to the window. 0 is a good lower bound. I'm going to go with -1 this time so I can see the y-axis. What's a good upper bound for x max? Is 100,000 good? Probably too much, right? Yeah, it is a little much. If the half-life is 30 years, let's just go out 10 half cycles or half-lives. So that would be 10 times 30, which is 300 or 3,000. You could always trim it off later. X scale to 0. Y min, I'm going to put -1 instead of 0 just so I can see the x-axis. And then the Y max, because this is decay, you should be able to figure this out. We started with 2,000 grams, so I'm going to go to 2,100, which is a little bit above that. And then I'll turn my Y scale to 0. You should see a relatively nice decay function. If you see too much horizontal, then make your X min a little bit smaller. If you don't see it tapering off, then make your X max a little bigger. All right, so now, since we have 31 included in our X window, we could just hit trace, type in a 31, and hit enter. So you get 977.159 grams, or what would it be if you rounded? 977.160, and you would need that 0. All right, so that's one way to do it. That's in grams. Remember, the other way to do it is straight from the home screen. You hit alpha trace, recall Y1, where we put our equation, type in a 31, and boom. Now it doesn't matter what the X window is. Okay? All right, so then the follow-up question here. If, in fact, 20 grams is going to be the smallest, the largest level at which it's considered safe to live in the area, then how many years is that going to take for us to get to that point? Well, in that case, now we're going to set C of t equal to 20 and solve for t. And so on your paper, you're going to show me C of t equals 20. And in Y1 or Y2, some place that's open, you already have, I guess, the other equation in Y1. You're going to type 20. If you hadn't set up your window yet, this is where you'd want to set up your nice window, hit graph, and it's going to be over here. If you want to see the blue line below the red line, you can kind of zoom in on that point, but the calculator should be able to handle it. Second trace, number 5, enter, enter, enter. It looks like they're kind of running into each other, but we know that they do intersect. So there it is. T equals 199.315 or 316, whichever you prefer. 0.315, and that's years. So it would take pretty much 200 years for this to get down to the safe level for habitation. And that would be in what year? If 1986 is when it started. Around 200 years later? 2186. Yeah, wow. Now, if you've ever seen any kind of a show about Chernobyl, there's this fallout radius, and it's heavily guarded. You can't really get in there without special permit. And there still are a few people that live there. I saw one little show where there was like a husband and wife goat farming couple that have lived there the whole time. And for some reason, they haven't gotten sick. Okay? Most people that were affected got sick. And so there's no new habitation that could take place there. But they are currently building a giant dome to cover up the reactor to try and contain some of the radioactive elements that are still high in that ground zero. And those people that are building it, they have badges and they check themselves pretty regularly throughout the day. Oh, how's my radioactive isotope level? And so hopefully, if they get that dome built, then maybe they could start building up around Chernobyl again, and you can have a thriving civilization there. And then, after 200 years, when the levels get safe, then maybe they can reuse the dome. They can, maybe bring in a football team or something, the Chernobyl isotopes or something like that, and reuse the dome. All right, but anyway, it's just another example to us. We had some information, we wrote the model, we predicted the y value by giving the t value, and we found the t value by finding the point of intersection with the given y value. Really the only two ways I can ask you to do something with it. All right, any comments or questions on Chernobyl, Fukushima, Japan? All right, let's take a stroll back to the previous section then when we did logistic. Logistic function, remember, is the modified exponential growth and decay. And the ones that we've seen, let me come up here in this little space. The ones that we've seen so far are logistic growth. So we had the rumor spreading. Remember that titanium nexus didn't really work. The logistic growth looks something like this. It grows at an increasing rate, and then right there it grows at a decreasing rate, and it approaches some limit to growth. I'll call it y equals L. And then there was always another horizontal asymptote down here at y equals 0. This point right here, where the graph was growing at its fastest rate, where the graph changed from concave up to concave down, we called that the what? Remember? Yeah, the inflection point. The inflection point is where the curvature changes. It's where the graph is growing at the fastest rate. And we know that it's always going to live at y equals what in relation to the upper limit to growth? At half of it, right? So if I call the limit to growth y equals L, this is going to be at y equals L halves, halfway. So that would be logistic growth. An application of logistic decay, which maybe you've covered it in maybe physics class, is an application that would look something like this. Something has an initial temperature and it cools as it approaches some lower bound, which is not necessarily 0. We'll call this y equals L. And there would be a horizontal asymptote up here. This would be similar to like Newton's law of cooling, if you've ever studied that. Newton's law of cooling. Newton got a lot of cool stuff named after him, right? Calculus, gravity, light, cooling, fig cookies. You got all the good stuff. If this would be a Newton's law of cooling, then you have like a cup of hot coffee that you set out on the counter. It's actually losing temperature pretty rapidly in the beginning, and then halfway between its these two horizontal asymptotes, it's going to start losing temperature more slowly because it's getting closer and closer to the room temperature, which would be the limit to growth here. So there are applications of logistic decay. You could even have logistic growth. Let me kind of just throw this in here. You could even have logistic growth equations with a y-intercept that starts above the horizontal asymptote. And then it's actually going to be decaying towards that. This would be like in populations of, let's say, wolves in a forest, right? The population that's maximum, the population amount that the forest can maximally sustain would be y equals L. And if you have populations of wolves underneath that, they're going to increase approaching the capacity of the forest. But if you ever put more wolves in than the forest can support, what's going to happen with the wolf population? It's going to decline. They're competing for resources now, and they'll still level off towards that carrying capacity. So logistic is pretty cool. So what we're going to do now on example 11 is we're going to write an equation of a logistic growth model given the following pieces of information. So just like we did with exponential growth and decay, we're going to write an equation. I will give you the template. F of x equals L over 1 plus C e to the negative kx. Just like when we did it for exponential, we were given a times b to the x. Remember, this was the exponential. So there are only two unknowns to find for the exponential. A, the y-intercept, the initial amount, and the base b. For logistic, we actually need three things. We need L, we need C, and we need K. So here's the format. Notice it's L over 1 plus C. C right here is not going to be your y-intercept necessarily, times E. The base is E to the negative kx power. All right, so I should have three pieces of information if there's three unknowns, and there they are. F of 0 is 20, F of 3 is 120, and the limit as x goes to infinity is 500. Do I know any of those unknowns immediately from the information given, L, C, or K? I do know what L is. Good, it's 500. Because that's what this means right here. If you hop on the graph for a growth function and you go out forever and ever and ever and ever, you're going to get closer and closer and closer to L. And remember, that is what's in the numerator. So we know immediately then that we can go for our model to be 500 over 1 plus C e to the negative kx. So we got one of them found, so we can jump to here. Now I just have to find C and K. Which of these two ordered pairs would be easier to plug in, 0, 20 or 3, 120? 0, 20. Now if this were exponential, we could call 20 right away the initial amount, right? If this were exponential, we would let A equal 20. In the logistic equation, though, you can't just let C equal 20 because it's not the same equation. It still is the coefficient of the exponential, but it's not the y-intercept necessarily. But you should still plug in the point 0, 20. So let me go ahead and denote that by saying at 0, 20, colon, we get 20 equals 500 over 1 plus C e to the. Now, if I plug in a 0 for x, what's 0 times negative k? K is a number. 0, right? What's e to the 0? 1. What's c times 1? C. So when I plug in a 0 for x, my k goes away, and I'm left with 20 equals 500 over 1 plus c. And now I just got to solve it for c. So here's a real quick way to do it. Multiply both sides by 1 plus c. It divides out on the right, and you get 20 times 1 plus c on the left. Now, instead of distributing the 20, which you certainly could do, go ahead and divide both sides now by 20. And you get 1 plus c equals 500 over 20. That's going to be a little bit easier to solve because 20 is a factor of 500. So notice what we essentially did. And this is a nice mathematical property that if you do it enough, you don't have to show that middle step. The 20 and the 1 plus c essentially did what? They switched places, right? They switched places. And algebraically, we know why that works. So you could go straight from 20 equals 500 over 1 plus c to 1 plus c equals 500 over 20. And I wouldn't need to see that middle step. Now, 500 over 20, that divides out the trailing zeros. So half of 50 is 25. Subtract 1, and you get 24. So c is equal to 24. So now we can go to this model. We can kind of build it as we go. Now it's going to be 500 over 1 plus 24 e to the negative kx. And now we just need to find the k. So now I need the other ordered pair. The other ordered pair is 3, 120. Move this guy over, move this guy over. All right, so at the point 3, 120, again, I'm indicating on my free response, I'm indicating what I'm doing. I'm helping someone navigate through my work. So I get 120 equals 500 over 1 plus 24 times e to the negative 3k. Now, to solve this one, it's going to require, without a calculator, it's going to require some knowledge of logarithmic properties, which we're not going to review until the next section. So guess how I'm going to expect you to solve that? Calculator. Yeah, it's going to be very easy. It's going to be just like a logistic equation from the last section. I'll graph the logistic right side in y1, I'll graph 120 in y2, and I'll just see where the two graphs intersect. And I'll walk you through that right now. So it doesn't really matter which one you put in y1 or y2. Let me go do it that way. I'll type in 120 in y1 since it does show up first on my equation. And then for y2, remember you're going to want to use the horizontal division bar, which is alpha y equals 500 in the top. Scroll down 1 plus 24e, which is second ln, to the negative 3x. We always use x as a variable. Now, again, if you hit zoom 6, that's not going to work. So you want to think of a reasonable window here. Negative 1 is good for our x min. We are measuring, well, we don't know what to do here. Let's let it be at 300. That's kind of something to play with, your x max. Your Y min could be 0. The Y max, we know that the top is 500. I'll go 600, giving it a little buffer. All right, now my red graph is my logistic. What do I need to do with my X max? Make it bigger or smaller? I need to make it a lot smaller. Notice it increased and then turned to the right close to the y-axis. So I need to kind of scale this down. Let me go to 20, see what that looks like. 20 is still too much, but I don't need to really mess around with it anymore in order to find my point of intersection. I can see the intersection point is right there. So now second trace number 5, enter, 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 and we end up with K equals 0.675. And so your final answer is going to be f of x equals 500 all over 1 plus 24 e to the negative 0. I like to put the 0 there, 0.675 x. And now you've written the equation. And we're done for the day, essentially. The last question on here, on example 12, I'm not going to work it. It is identical to the last question in the notes from the previous section. The only difference is it's swine 09 instead of titanium bracelet rumors. But remember, your free response will be like the last example. We'll quiz tomorrow. Probably not going to be over logistic. It'll be over exponential growth or decay. And the worksheet is going to be due tomorrow. Okay? All right. So again, if you want to do example 12 on your own, that's good practice for the test. You can compare it with the notes from the last section, the very last example. All right, we're done.